He's from Universidade Federal de Viçosa, who will talk about on the envelope of intermediate lines of plane curves. Thank you very much, Mostafa, for accepting our invitation. You can start when you are ready.
Well, hello everyone. First of all, I would like to thank the organizing committee, especially my friend Georgie, for this invitation. Really, it's a great pleasure for me to be here with you guys. Well, as Georgie told, today I will talk a little about a topic titled by Envelope of Intermediate Lines of Plane Curves. This work actually is a joint work with Professor Adi. He's from University of Viçosa, and also his ex-student, Diego Trindade. I divide this presentation in four sections. First, I will talk a little about introduction, objective, and then I will talk about the main idea of this work. Well, our research took place in the field of differential geometry, particularly in the non-Euclidean geometry known as affine differential geometry. Our concentration here is to study a certain set of plane which is affine invariant, and it's obvious that we want to study the local behavior of these concepts using some singularity theory. It's worth mentioning that this work is published in 2020 at this journal of results in mathematics, and I should emphasize that this work was the master dissertation of Diego. So if this work seems very easy for you, I do apologize. Well, suppose that gamma is a plane curve. Our goal here is to study the envelope of a family of intermediate lines. What is envelope? What is intermediate lines? I will define later. Our idea was to generalize the concept of midline of a plane curve, and we are going to study the envelope of this family of lines which we call intermediate lines. Well, to do this, it's very common that usually we use a parametrization called affine arc length parametrization for curves. A parametrization is called affine arc length if it satisfies this equality. It means that the determinant of first and second derivative of gamma with respect of this parameter s should be 1. Well, here I bring the definition of affine arc length function. To be more precise, if gamma has arbitrary parametrization T, to obtain the arc length parametrization, we just simply calculate this equation, and the affine arc length parametrization will be this integral of the determinant of first and second derivative of gamma to the power of 1/3. Well, the affine arc length parametrization has this advantage for us to, in this case, the affine tangent vector is simply the derivative of gamma with respect to S, and affine normal vector will be simply the second derivative of gamma with respect of S. But if gamma has an arbitrary parameter, then the affine tangent and affine normal has a little completed formula. Here is K, the capital K is the determinant of gamma, the first and second derivative of gamma with respect of the parameter T. Well, another aspect that is very important in the study of affine geometry is affine curvature, which if we parameterize our curve by arc length parameterization, the affine curvature is simply the determinant of second and third derivative of gamma. Well, there is a well-known theorem that says that gamma has constant affine curvature if and only if gamma is a conic section. For example, if the affine curvature is negative, 0, or positive, so we have hyperbola, parabola, and ellipse. Well, another concept in affine geometry and in study of plane curves in affine space is affine evolutes. If gamma provides the arc length parameterization, then affine evolutes is the locus of centers of affine curvature. The parameterization of affine evolutes is simply similar to Euclidean evolutes, but here we have affine curvature, here we have affine normal. Well, another aspect that you know better than me is the concept of contact geometry. If we have two curves, gamma and F, we say that these two curves have K contact at point T equal to 0, if the contact function has a K singularity, and if we drop the last disequality, then we say that these two curves have at least K contact, K contact. Well, the envelope actually, or discriminant for a family of sets, a family of curves, a family of functions, is simply the set of all variable x, such that the family and its first derivative is equal to 0. An easy and famous example of envelope is the family of circles. It's really easy to calculate the envelope or discriminant of this family, and we reach, for example, these two curves as the envelope of family of circles. Well, now I'm going to talk a little about what's a midline and what is the envelope of midlines. Well, consider gamma a closed curve. We consider 2 points P1 and P2 in this curve. The midline in these two points, there are three possibilities for these two. The first possibility is the tangent of these two, the tangent curve at the tangent at these 2 points have intersection. or these 2 points can have the parallel tangent, or these 2 points exactly are the same. In the first case, the midline is the line that passed through the intersection point and exactly the midpoint of these segments P1, P2. In the case when 2 tangents are parallel, the midline is the parallel line which passed through the midline M. And in the third case, when 2 points coincide to each other, the midline for us is actually the normal, affine normal line. Well, for each case, we can calculate the envelope of family of these lines. This is I forgot the reference to put reference here, but this is famous that in the first case when tangents are non-parallel, the envelope is a set called affine envelope symmetry set, which is the closure of the locus of the center of conics, which have at least 3 contacts with the curve at 2 or more distinct points. For example, for this oval, the affine envelope symmetry sets gave us these red curves. Well, in the second case, when we have parallel tangents, the envelope of midlines here are the parallel line which passed through the midpoints. The envelope of family of these lines give us exactly this. For this example, for example, give us this blue curve, which we call it midpoint tangents locus. This is the locus of midpoints of the locus of midpoints exactly give us this envelope. And in the third case, when the midline is exactly the affine normal line, the envelope of affine normal gives exactly the affine evolute of gamma. Well, there is a theorem that says that, well, in this case, the envelope of midlines actually is the intersection, the union of these 3 sets. And the interesting thing here that these sets connect at singularities, and so everything is very nice in this case. Well, now we are going to define a kind of generalization for the concept of midlines. We are going to define a new family, which we call the intermediate lines, and we are going to study the envelope of this family of lines. Well, here again we have 3 cases. When we have a curve, a closed curve, we take 2 points, P1 and P2, and these 2 points, there are 3 possibilities. They can have tangents can have intersection, or their tangents can be parallel, or these 2 points can coincide with each other. In the first case, simply here midline was this point, the midpoint. Instead of this point, now we take a different point, which we call M alpha in this segment. The idea was very simple. We take this point we call intermediate points, and we connect this intersection with these intermediate points. We connect these two together, and we study the envelope of this family. This is really a simple idea. Well, in the second case, when we have tangents are parallel, the midline again is the parallel line that pass through the midpoints and is parallel to the tangents. And in the case that 2 points coincides, the intermediate line is tangent line at the points P1. Well, now we are going to study the envelope of this family of lines. Okay. And we study this case by case, and we study local behavior of this set, and it's just a game, and it's not a very complicated aspect. Well, in the first case, when we have non-parallel tangents, we consider gamma 1t and gamma 2s are local parameterization around P1 and P2. We consider local parameterization around each point, and simply the intermediate points for alpha in between 0 and 1, the intermediate point is the point this point. Well, when alpha is 0, we have at P1. When alpha is 1, we are at P2. Well, a very common and well-known concept that we use in the study of affine geometry are affine conormals or conormals. Conormals are actually some functional that the definition of conormals are given like this, and these guys have this property that they when they act on a tangent vector, the result is 0, and when they act on a conormal vector, the result is 1. This we call conormal functions. Well, using conormals, we will define the equation of line here, and then we are going to study the envelope. For study the envelope, we need to know about the derivative of these functions as well. So in this lemma, we simply calculated the derivative of conormals with respect to parameterization around the point. And then this is the equation of line, the intermediate line, the line which passes through the intermediate points and the intersection points. Well, here C is the segment, the chord connecting points P1 and P2. It's a vector. Well, now we will consider the family F, which is this family of the zero of this family is exactly the line, and we are going to study the envelope of this family. Well, the calculation is really simple using that lemma that I mentioned before. We found a necessary and sufficient condition for a pair S and T, where parameterization around the point P1 and P2. We find a necessary and sufficient condition to the envelope has solution. We need this relation between conormals, which here lambda is given by this formula. This is really important. Using this necessary and sufficient condition, we relate the parameterization S and T. Well, this can be simplified if we consider arc length, affine arc length parameterization. This lambda with affine arc length parameterization simplify to this formula. It depends only in alpha, and in this case, this condition simplifies to just to find the determinant of this matrix. Well, and now considering this relation between conormal nu1 and nu2, we can calculate the envelope, and we find the envelope, this capital X is actually the envelope of intermediate lines with non-parallel tangents, is given by this formula. Well, in this case, we just say the envelope of intermediate lines, we call them a affine envelope of intermediate lines, and it's denoted by AEIL. Well, I put two remarks here. If we consider if both points have arc lengths, affine arc length parameterization, this envelope simplifies by this and gives this is the actually the envelope, and this, when alpha is exactly the midpoint, this is exactly the result is exactly the affine the envelope of midpoint, which I said before. Well, now we are going to have fun. We are going to study the local structure of envelope. This is really not difficult. We consider initially we will present a local model for a smooth plane curve, which will be used to understand the local structure of the envelope of intermediate lines. Well, locally, first we consider these two cases. Sorry, this case when the point P1 has nothing geometrically important. It has no inflection, it has no vertex. And we consider the local parameterization around the point P1, but P2, we choose a general parameterization for P2, and the rest here really is the matter of it's just for us. It's just a game. We consider, for example, some conditions when we have the envelope are regular, where it's singular, where we have singularities of type cusp, where it's 3-4 cusp, and so on. By using this parameterization, we should have the parameterization for our family of lines. This F now is the equation of intermediate line, and this condition, the condition for the existence of solution, simplifies to this determinant should be 0. That necessary and sufficient condition, which that theorem that I mentioned before, and using this, we find a relation between parameter T and S, and then this is the relation between parameter T and S, and then we apply this to the envelope, and we find the results. Well, for example, we found that if P1 and P2 are not inflection points, and the regularity condition for the envelope of the family of intermediate lines is given by these two formula. Alpha shouldn't be these two numbers, and B3 should not be this value. Just remember that B3 was the coefficient of cubic parts of parameterization, and B1 should be difference 0. This is a condition also we suppose. Well, or for example, if P1 is an inflection point, then the envelope of family of intermediate line is regular if B3 is difference 0. Equivalently, if P2 is an inflection point at the origin. Well, the second case, when we have non-coincident parallel tangent lines, the envelope of intermediate line, again, we do the same process. We find the family, we find the necessary and sufficient condition, then we calculate the envelope set of this family of lines. And for example, here in this case, we find the relation locally between T and S, and then applying this relation to the envelope, we reach some condition. For example, regularity. In this case, the envelope is regular if and only if B2 is different this value, or we have ordinary cusp if and only if B2 is equal to this one, B3 is different to this one, A3 is the coefficient. You know, this is the relation between geometry of locally, the geometry of this point and the geometry of the envelope. And also we studied the 3-4 cusp as well. Well, again, here we can consider the inflection points as well. We consider if P1 is inflection, then we have another condition for regularity, and for example, here this proposition says that the envelope, the inflection, then the envelope passed through the midpoint is regular if alpha is different to half. I forgot to put this here. And if B2 is different from 0, then the curve gamma has an inflection of order k at P1 if and only if the envelope has inflection of order k at the origin. Well, in the third case, just remember in the case of midline, the third case, the midline was the affine normal line, but in our case, the intermediate line is the tangent line at the points, and the envelope of intermediate line in the third case is the curve gamma itself. And we did this calculation. I don't want to enter to details. And we have this theorem that says that when we have 2 points, P1 and P2, P1 is parameterized by parameterization T, P2 is parameterized by parameterization S, and we try to tend S to T. This means that this point is going to, these 2 points are going to be coincide. The intermediate line in this case tends to tangent line, and the envelope of tangent line is the curve itself. This is the difference between midline and intermediate line. In the case of midline, the envelope gave us the affine evolute, but here we have the curve itself. The same example that's here is the case of midline. These 3 curves coincide, match exactly very beautifully, but in the case of intermediate line here, for example, is for alpha equal 0.6, we reach to this curve. As you see, this curve can have self-intersection, can have many geometry here, and the third case is the curve itself. Well, finally, we can say that in our case, when we have intermediate line, alpha is not the midpoint. The envelope is the union of the envelope of intermediate line is the union of these 3 curves, which the third one is exactly the curve itself. But in the case of midlines, we have these 3 union. Well, it is natural when we have alpha, our family has alpha as a parameter, it is natural to ask now, when we perturb this family around alpha, perturb alpha, then what's the condition of versality? Here we study this question. Again, we have 2 points, and here we suppose that at the initial points we have a singularity of this curve, the envelope has singularity of case A2, and we prove that this family is versal if and only if we have this condition. Just remember that A3 was the coefficient of the cubic term of one of these points, for example. B1 was the linear term of the other points. So versality and the geometry also here are related. Well, that was all that I prepared for today. I should emphasize that we also study that the condition that this family, when it has, for example, cuspidal edge, this family in R3, considering alpha also as a variable, when this family has cuspidal edge, then we have a big leap, and but I decide to not mention these results here. And that was all I have for this presentation. Thank you very much for your attention.